Okay, this was requested from you. I mean, I'm just following the list, but let me know if it's not the question. This one is summer 23, paper 4-2, question 3. Although I do not see it in your screenshots. So I'm not sure whether it's the question you intended to ask. Maybe you can let me know. If not, just proceed lah. Okay, so all right. So this question, right, is about the thermodynamic cycle. And I think I will also screenshot the questions and send it into chat for everyone in case you want to doodle on it. So it's about the first law of thermodynamics. And then when they ask you to state the first law, which is basically delta U is Q plus W. But I think when you identify the symbol, be a bit careful because the term change, right, is only implied for internal energy. So delta U here means change in internal energy. Don't go and spam the word change for every single term. That would not be recommended. Okay, and then Q would be heat or thermal energy transfer. And W will be work done. Since I put positive, so I'll put work done on the system. So please don't write change in thermal energy, or change in, or change in work done. Cannot. Okay. All right. So moving on. Here you have a cycle. It's a slightly different one. Normally you will have a triangle looking cycle, but sure. Complete table 3.1 for all the changes by placing 2 ticks in each row. Okay, very nice. So let's look at A to B first. From A to B, the volume is decreasing, right? You can see the volume is decreasing. So AB volume decrease, gas is compressed. So work done on gas, positive W. Positive. All right, and what about B to C? B to C volume is constant. It's fixed at this particular volume. So the work done on the gas is 0. Okay, so this one is easy to answer. The harder to answer one is the change in internal energy because you will need to involve your delta U, which is Q plus W. And this change in internal energy, delta U, is also the sum of the distribution of kinetic energy plus potential energy. And this kinetic energy is proportional to the temperature. So I guess to know whether when we move from A to B, whether there's a change in internal energy, because this is ideal gas, potential energy is 0. So this one is basically equal to 0. So right now, when I decrease the volume of the gas, the temperature decreases. So from AB, not just volume decrease, temperature also decrease. You might be asking me, Cher, how do you know? Well, there are a few ways to tell lah. Because for AB, the pressure is constant, right? So if I use the ideal gas equation, PV over T is PV over T. V1 over T1 is V2 over T2. Okay. Or in other words, V is directly proportional to T. So I know the volume at A is less than the volume at B. So because of this, the temperature at A will be less than the temperature at B. But if you have read or studied my notes, you will understand that I tend to draw isotherms. So I already can tell that this one, AB, the temperature decrease. So if the temperature decrease, this means the change in internal energy decreases. I can't really use the first law of thermodynamics, although they asked me to state, because I don't have information about the heat transfer. I only have information about pressure and volume, and sometimes information about temperature. Okay, so let's consider B to C. From B to C, volume constant. That means P over T, P1 over T1 is P2 over T2. So P is proportional to temperature. So since P is proportional to temperature, you can see the P pressure increases. Pressure increase. PB is less than PC. So the temperature at B will be less than the temperature at C. So that means C is hotter. You can also see that we have moved up an isotherm. So what isotherms are, although it's not in your syllabus, but it's a useful thing to pay attention to, is we can draw all the lines where the gas have the same temperature. The line underneath will have a smaller temperature. Let's say this is 200, 300, 400 Kelvin. Okay. Yeah. So that lah. Okay. Anyway, so I know for a fact that from B to C, temperature increase. Okay. You can also use logic one. If the volume of the gas chamber is the same, and I want the pressure to be greater, I must increase the temperature, make the particle move faster, increasing the number of collision. Just like from A to B, if I'm compressing the gas, but I don't want the pressure to increase, then the particles have to move slower. Temperature will decrease one. Okay. So it just depends on how familiar you are with the modeling of gas particles in your brain. Right. So use the first law of thermodynamics, which is your delta U is Q plus W, to describe and explain the energy transfer associated with one complete cycle, A, B, C, D to A. So they want one complete cycle, meaning if I cycle one round, is there heat gain or heat loss to the system? So maybe I will screenshot and put the graph here so we can doodle on it. So the question is basically asking us, after one cycle, from A to B to C back to A, B, C, D, A, is there energy transfer in or out? Okay. So since I'm going to use first law of thermodynamics, I'm just going to talk about the internal energy and then Q, W, then I conclude with Q. Let's talk about delta U first. Okay. So to describe delta U, I would say that you have just completed one cycle, right? So in one complete cycle, the gas sample returns to initial state, which is A. A, B, C, D, back to A. So because of this, the temperature returns to the initial value. There is no change in internal energy. Okay. So generally, one term will have 1 mark, that's why it's 3 marks. All right. Then we can look at W so that we can conclude Q. Let's consider W. To consider W, I will need to consider the area under the PV graph, right? So WAB is this one, this area. And because volume decreases, this is positive WAB. Okay. And then there is another work done when you go from C to D at a higher pressure. And when you go from C to D, your work done is this entire area, or this whole thing. And it's negative, right? Because the gas is expanding. So for this is your WCD. And it's negative lah, because the volume decrease. So I will say that there is more work done, gas expand, so work done by the gas during the process CD compared to work done on the gas during the process AB. And because of this, the net or the resultant work done of the cycle is negative. Because the negative area is bigger than the positive area. So let's rearrange my delta U first. Delta U is Q plus W, but Q is equal to delta U plus, or not plus, delta U minus W. So right now, my W is negative. So it becomes delta U minus negative W. Okay, the net work done of the cycle is negative. You have a negative here. Okay, so negative, negative, positive, but this delta U is 0 lah. So your Q is positive W. So hence, you don't have to show this. You can just deduce, because we can already tell net work done is negative. If delta U is supposed to be constant, or 0, sorry, if this one is equal to 0 and this is negative, then Q must be positive. You can tell even from the first equation. Or you can rearrange, like what I did. They are both fine. So for here, I'll say something like, from here, your Q is greater than 0, or your Q shows that there is a thermal energy transfer, or just simply energy transfer into the gas system. So in paper 4, get ready for them to ask you to describe something that they've never asked to describe before, but be assured that you are able to do the analysis if you give yourself enough time and enough familiarity. Because normally the first law of thermodynamic question still works the same way. Look at the situation and analyze what happens to the internal energy. Internal energy is always linked to temperature. Look at the graph and look at the situation and think about W. W is always linked to change in volume and area of your PV graph. So in this case, you will need to refer to the PV graph. Okay, then from there, you can just put everything together and try to solve the problem lah. Okay. How do we know we should compare work done? Because when I first read this question, your first thought was not to compare the work done. Then your first thought is to do what? What would your first thought be? Your first thought may work. It just depends on whether it links to a comparison. I just mentioned, if you just mention A to B and B to C, then you never mention C to D and D back to A, you basically didn't answer the question, right? So my suggestion is read the question, describe and explain the energy transfers. So these are my description. Description number 1, no change in internal energy. Description number 2, the net work done is negative. Description number 3, energy transfer into the gas system. With explanation. So the only way to know is to practice. So some student may not think to compare the work done, but then when they write this equation, immediately what should come to mind is if this delta U is 0, and I want to know whether this is positive or negative, because that will tell me whether the energy is transferred into or out of the system, then I probably need to know, is this positive or negative? Then I look at the graph, because it starts with the first law. So this is my first law of thermodynamics. I start with the first law. So basically, I will doodle at the side one. Okay, this delta U is constant. I don't know about Q, but what about W? What about the work done there? Okay. Of course, you could say, teacher, what about the work done from BC and DA? This work done is 0. Work done from BC is 0. There is no change in volume. The work done from DA is also 0. Does that make sense, Glenn? There is no certainty to make sure you have the experience to handle by seeing every question before. That is totally not possible. Physics is like that one. So what you could do is you could try to respond to the question. Just like if I learn martial arts, there is no certainty that the next person come and attack me. I know how to defend. But I've do so many drills before, every day, every 2, 3 weeks, I show up in the gym, I spar with my friends, I spar with my gym mates. So hopefully there's a neural pathway in my brain. Then someone jump scare me, I know what to do. So it's partly reactionary, partly experience, and also partly responding to the question. So I respond to the person that come towards me, whether they're going to my throat or trying to snatch my bag. I don't know. Get my point? So physics is like that lah. It's a subject that has very little. Okay lah, I won't say very little. They will provide some familiar question, only as to not make the whole paper too complicated. But overall, we will have wildcard questions. The only way to do them is to breathe, look at the question, try to give them what they want. If you write this one or you totally don't know what to do, you do the other parts first, then you come back again. This is only question 3. Okay. The next one that we have is Winter 2-3, question 9. 9. Right, something need to chat now. I think the first part is fairly straightforward. You want to talk about binding energy. So this one is, let me write down the year first. Winter 2-3 P41. Question 9D. So the first part, when you define nuclear fusion, here are the keywords. Make sure you mention that it is 2 smaller nuclei joined together, combined together, fused together to form a larger, more stable nucleus. I add the more stable for my brain. Okay. Then when you draw the binding energy per nuclear number, there are certain spikes, but we don't care about that because it's not chemistry paper. So generally, your trend should be like this. Make sure the line is steeper at the beginning and smaller at the end. And do not touch the axis, okay? There's no such thing as a zero binding energy, especially for the bigger particles. Okay, so what you care about is a turning point. Please label the turning point here to be 56. It should look like 56, which is 1/5 of the scale each, roughly. 2 marks. 1 mark is for the shape, 1 mark is for the position of the turning point. Label point X that could undergo alpha decay. So alpha decay is normally when the nucleus is too large. Too large means larger nuclear number. Anywhere here, X. And then point Y, or you could just make a mark here, just mark it down, this X. Point Y represent undergoing nuclear fusion. Fusion is when the nucleus is too small. So somewhere here, Y. Don't put here. This one quite stable already. You put Y here a bit wrong. So you should put when the binding energy is low. In fact, the lower the better. Hang on. Maybe I'll put my X here. For the big nucleus is not really an issue. It's the small nucleus. Small nucleus themselves are very hard to fuse together one. As I don't know whether you recall, normally it only happens in the sun. So in the sun, the Y value is very small. Okay, so closer to 1. Okay, let's look at part D. So part D shows a nuclear fission, splitting of the atom to form strontium-93 and xenon-139. I can actually calculate, or rather calculate the proton and nucleon number. 93 plus 139 plus 2 minus 1. This is 233. 38 plus 54. This is 92. So I balance the proton number and the nucleon number, just in case. But right now it says that the fission of 1 mole of Z releases this much energy. So it looks like I need the mass number of Z. Okay, Z consists of 233 nucleons. So sometimes the question won't directly tell you need to find the nucleon number. In fact, this is 4 marks, so there's probably some hidden steps that I need to do before I can arrive at the answer. And I'll figure that out once I look at the data given to me. Okay, so it's not straightforward, but it's okay. Trust yourself, you can do it. So I want to find the binding energy per nuclear number. So let's assume this is your end goal. I want to find binding energy per nucleon. This is good enough already. I know I have to divide by 233 already. Okay, but I want to find the binding energy of the reaction first. Okay, so it says here that 1 mole releases this much energy. Can I find the amount of energy from 1 nucleus? So in case you don't know, 1 mole is Avogadro constant number of nucleus, which is 6.02 times 10 to the power of 23. Okay. Because instead of using this number, we just treat it as 1 mole. So from here, hence, the energy released due to the fission of 1 a single nucleus of Z would be 1.77 times 10 to the power of 13 divided by the Avogadro number. I can press calculator if I want to And leave it here because later I'll probably need to use it anyway. Okay. So this is the energy release of a single nucleus, but a single nucleus also imply a single reaction lah. All right, a single reaction of decay. Number two. I also know that energy released in a single reaction is the difference in binding energy, which is basically the binding energy of the product minus the binding energy of the reactant. This is in Joule law. So I know the energy released. Energy release here would be 1.77 times 10 to the power 13. I don't want to press my calculator first simply because I don't want to round my numbers first. I want to have them there. Okay. Binding energy of the product. Product is strontium and xenon. Of course, you could ask me, but sure, product is strontium and xenon and two nucleus, correct? Two nucleus is free. They are not bound to anything, so no binding energy, these two. They are not a nucleus, they are not bound to anything. Whereas all the 93 nucleons in strontium is stuck together and 139 xenon is stuck together. Okay, so I'm going to put that in. 1.25 times 10 to the power negative 10 plus 1.81 times 10 to the power negative 10. So the reason why I'm doing this is because I want to maintain everything in Joule. I'll convert later. And what am I looking for? The binding energy of the reactant. Who is the reactant? Nucleus Z. Okay. Nucleus Z is not this one, is what? Is the reactant. And once again, this one neutron has no binding energy. All right, so I'm looking for the binding energy of Z. I guess now I can press my calculator. The binding energy of Z be 5. So I'll have 2.766. I'll write one extra SF first because this is not my final answer. Negative 10 joule. Okay. But I want to find binding energy per nucleon number and I want to convert these to mega eVolt. That will be step 3. Binding energy per nucleon number. So my binding energy is 2.77 times 10 to the power negative 10. I want to convert this to mega eVolt, so I'll convert this to eVolt first, okay? Which is 1.6 times 10 to the power of negative 19. So once again, joule, convert to eVolt divided by E. This is the E that I divided. Okay, what's my nucleon number? My nucleon number is 233. Of course, since it's part of the working, I show how I got 233 in the first place, right? I took the mass number of 93 plus 139 plus 2. 93 plus 139 plus 2 minus 1. Just show the working. 93 plus 139 plus 2 minus 1. So this will be 223. Or I guess you can press your calculator, which I'll do so now. This will give me 7.419 times 10 to the power of 6, or 7.42 mega eVolt. 419. If you start rounding from the beginning, meaning from here you already round already, that's fine. As long as you write one extra SF. Our final answer must be 3 SF because the data given to us is 3 SF. You see this? 3 SF, 3 SF. So we need this one to be 3 SF. So if I want to write my final answer as 3 SF, if I press an intermediate value like this one, it has to be at least one more SF. 3 plus 1 SF. If you're not ready to press a calculator and you just, you don't want to round, then you just stuff all of it inside one calculation. So it's a matter of preference. Okay. If I actually type 2.766, this one is 4195, so 420. But if you round earlier, you can get 43. It's okay. Just make sure you show all your calculation. So to answer the response, how do I know? Well, to be honest, when I start the question also, I don't know. I'm just trying to put together the information so I can give it back to them based on what they give me. So if 1 mole, I figure out most of the time I calculate reaction is for 1 particle, so I try to find the energy of 1 particle. And then the energy release, which is the energy of the reaction, is always the difference between product minus reactant. Yes, it's always product minus reactant. Because it is becoming more stable. Just product minus reactant. Don't worry too much about the exothermic and endothermic. So just a recap. Energy release in the nuclear and the nuclear reaction can be delta mc square. But this delta mc square is the mass of the product minus the mass of the reactant. Depending whether it's in terms of U or not lah. Don't know, depends. I will just put C square here. Kg, then no need U. If it's not Kg, then you put the U. Okay. This delta M C square can also be the mass defect of product minus products, one more than one, mass defect of reactant, C square. So this delta M can look different one. The most obvious one is the first one, mass of product minus mass of reactant. But it can also be mass defect of product minus mass defect of reactant. Don't forget to multiply C square lah. And if you look at today's question, mass defect times C square is actually binding energy of products. Right? Mass defect times C square is this one. But basically just open up the bracket minus the binding energy of reactant, which is also mass defect times C square. When you have a product minus reactant, you can omit the sign if the sign is a concern for you. Because this is not chemistry, so most of the time we allow you to drop the negative sign. Does this one have a negative sign? I don't think so. 1.77. Yeah, it does not. So the implication of this, just to continue this line of inquiry, is if the mass of the product is greater than the mass of the reactant, this also will apply to mass defect. It will also apply to binding energy. This one means that the reaction releases energy. And because the reaction releases energy, the reaction, sometimes the word that they like to use is energetically possible. Meaning it's possible to happen on its own, spontaneously, and it happens in nature, which is generally the reaction we study in physics. Okay. I'll do one more. Winter 22. P4. Why do I feel like I've already done this question? This one is ON 22 P42. Question 9A. Okay, I think the first part is pretty standard. You are just trying to write down the explanation of what discrete lines mean to provide evidence for discrete energy levels. Okay, so refer to the mark scheme. Amber is asking A part 2. Show that the energy level is negative 1.51. Well, you see, this is the wavelength that is part of the emission spectrum of hydrogen gas. So you have a few wavelengths, which I'm going to copy over and put here for you to see. Okay. So each value of this lambda corresponds to 1 photon. Right? This is what you will write here. That's why the explanation is supposed to help you understand the question. So maybe I'll briefly write down the answer. So I will say each electron transition as emits single photon where its energy is the energy difference between the energy level. So basically saying every electron transition will emit a photon. The photon is equal to the change in energy level. This part okay or not? So it's time to transition. And of course, then to complete the question, you will then say, well, since the energy levels, the energy of photon have a discrete wavelength, as you can tell from these discrete lines, only got 488, no 488.5, no 480. So delta E is discrete. Don't use symbol in the exam, write full terms. And because of this, the energy levels are discrete. Okay, so we're going to transition, okay? Transition to 3.4. So I'm going to transition to this point. What are the possible ways I can jump down to here? Can transition this way, can transition this way. Maybe I'll change color. Can transition this way. I can transition this way. I can transition this way. I can transition this way. Okay or not? So because I can transition in all these different ways, I can say that, let's say I label each delta E. This is delta E1, releasing a photon of lambda 1. Photon. Likewise, if I jump from the second layer, delta E2, releasing a photon of lambda 2, delta E3, releasing a photon of lambda 3, delta E4, releasing a photon of lambda 4. So in ascending order, delta E1 is the smallest, and delta E4 is the biggest. The energy jump, okay? I know that the energy of the photon, which is the same as my delta E, is hc over lambda. So this means the greater the delta E, the smaller the lambda, implying that lambda 1 is greater than lambda 2, is greater than lambda 3, is greater than lambda 4. Which delta E should I care about? I should care about X, because they want me to find X. So I'm going to care about delta E1. Delta E1 will have the largest lambda. So lambda 1 will be 658 nanometer. Lambda 2 is 488 nanometer. Lambda 3 is 435 nanometer. Lambda 4 is 411 nanometer. Okay. Then I just continue only, delta E, the change in energy level, is equal to the energy of the photon. I care about the energy of X transitioning to 3.400. Energy of photon is hc over lambda. I got no space, I wrote down here. Hc over lambda would be 6.63 times 10 to the power negative 34, 3 times 10 to the power 8 divided by 658 nanometer. Is that okay, Amber? Then from here, you can calculate your EX. Don't forget to convert this to eVolt as well. So let me move here so I have space. I need space. Needs to be converted to eVolt because this is already in eVolt. 0.6 times 10 to the power negative 50. So you should be able to interpret the spectrum. Please don't, I don't know how they will transition the electron during the exam. So you need to read the data given in the question. I think this one they ask again in FedMarch 2-3. Then you press your calculator, you get your EX, which I presume is negative 1.51 eVolt. Let me know if there's any follow-up questions. Right, very good. Because this one basically goes EX plus 3.400 is 1.889. So this will be 1.510, 511. Okay, moving on to the next thing. By the way, those of you who haven't tried this question yet, you should, because they tie this to the Doppler redshift. Yeah. This is the original value of your wavelength. See, all red shifted into the red zone. But again, it's just interpreting the pattern. And if you've done the FATMARCH 2-4, instead of giving you the pattern, they ask you to draw the pattern. Okay, lor. Very doable. Question 6C. Okay, this one is a bit of a question that's a little bit different than what we're used to. Okay. So the first part should be trivial. As a form of exercise, we write lah. Okay. Potential is work done per unit positive charge. When it is moved from infinity to a point in the electric field. Okay, so part B, we have an isolated conducting sphere in a vacuum. It has a radius r. This is a very standard derivation. Okay. Initially, it is uncharged, so Q is 0. It is then charged by friction. Maybe I rub on the dome, or I put a belt inside like a Van de Graaff generator, but it has a final charge Q. Now the charge is Q. So start with 0, now the charge is Q. This charge can be considered to be acting at the center of the sphere. Yes, we can, because of how the charge distributes itself along the surface. We can assume that all the distances we measure from the center. So by considering the electric potential at the surface, show the capacitance is given by this equation. So this is a standard equation. We can use Q is equal to CV to start off, but V is equal to Q over 4 pi epsilon naught. So I can substitute Q inside 4 pi epsilon naught R, where R is the radius of the sphere. So this is radius, this is the V at the surface. So at the surface will be a distance of radius R from the center. But regardless, we can cancel the Q, and you have C is equal to 4 pi epsilon naught R. So in part C, we are going to work with this dome or this sphere. This first sphere has a radius of 13 cm. It is inertially charged so that the potential at the surface is 4.5 kilo. Okay, so I have the first sphere. Let's call it sphere 1. The radius is 13 cm. And the potential at this surface is 4500 volt. A smaller isolated sphere, okay, I have a second sphere, of radius 5.2 cm, initially uncharged, is brought near to the dome. Okay, so right now the green color dome has no charge, but the blue color dome has a lot of charge. Lots of charge. Wow. So all these charges, they don't like the fact that it is so positive. It wants to be neutral. So it's going to look at this green color dome and go like, hey, you're very neutral, huh? You got a lot of extra electron, huh? Can I yoink some away? It's neutral, so positive and negative charge is the same. Okay, so the negative charges will be more attracted to this one, so it will go this direction. let's assume that the blue sphere is charged positive, although it does not matter. The reverse also can happen. So you get a zap. Zap. They will zap them. The current, the sparking will flow until they reach the same potential. So currently, the potential here is 0 volt. And after some charge transfer, the potential in the big sphere here, let's say this is V1, it is less than 4500, but I don't know what is V1. And this second sphere here will be V2. It will be more than 0, but I don't know what it is. V1 is equal to V2. Sparking will stop. So there's less positive charge here. Okay. And then this one also will be charged slightly positive because it lost some electron. Like that. So V1 equal to V2. Until they reach the same potential. Full note here, V1 is less than 4.5 K. V2 will be less than 0, greater than 0 volt. Calculate the charge that is transferred between the two spheres. Okay, how about we start with what we know? Number one, from conservation of charge, the total charge between both spheres will be the same as the initial charge on the first sphere. Of course, you could then say, "Sure, can I calculate the charge?" You can, you probably need to. So I can use V is equal to Q over 4 pi epsilon naught R on the first sphere. Okay, this is the initial charge. So here will be 4500. This is Q. Your 4 pi epsilon naught is up to you. You can just put 8.99 times 10 to the power 9 here. You can put the whole 4 pi epsilon naught in, also fine. Over, what's my R? My R is 0.13. So from here, I can calculate my Q. My Q would be 6.507 times 10 to the power -8 Coulomb. I'll write extra SF because just in case this is not my final answer, but writing 6.51 is also okay. Right, so this is what I know. I know the total charge is this much. I know that eventually this charge Q1 is your 6.507 times 10 to the power -8, but Q2 is 0. So I know Q2 will have more charge and I know Q1 will have less charge. I just don't know by how much. Right. The second thing I know is this one. V1 is equal to V2. So point number 2, the sparking will stop when the potential difference of the first sphere is equal to the potential difference across the second sphere. And to think about V1 over V2, I can use Q1 over C1 is Q2 over C2. The new charge lah. So I can find Q1 here and find Q2 here. This is after sparking. So we have a few issues here. Number one, I don't have the capacitance, but they did ask me to derive this equation. So I can use it there. Okay, so up to you. I don't know whether you can tell C is proportional to R. So I can just substitute R inside one. Q1 over C1, which is R1, is equal to Q2 over C2, which is R2. Nah, your 4 pi epsilon naught can cancel. Don't write also, never mind. Okay. So from here, Q1 over the 13 cm is Q2 over 5.2 cm. So I think I'll just bring the 13 over now. So from here, Q1 is equal to 2.5 Q2. Makes sense because 1 is a bigger surface area. So it should be able to accommodate more charges. So here is what we know so far. I know the total charge is this much. I know that the charges are redistributed at this ratio. Can I find Q1 or Q2? Can. So hence, Q1 plus Q2 is 6.507 times 10 to the power negative 8. You see, it says here that I want to find the charge that is transferred. So in order to find the charge that is transferred, I either find Q2 or I find the total charge minus Q1. Because Q1 has all the charge, okay, transferred between the two spheres. Okay, anyway, let's calculate first. From here, if I want to look for Q2, I should substitute Q1. Okay, 2.5 Q2 plus Q2 is 6.507 times 10 to the power negative 18. So Q2 will be this answer, 6.507 divided by 3.5. So this will be 1.86 times 10 to the power of, why I put 18, negative 8. Hold on. So I find it easier to start with what I already know. There are many ways to do this question now, okay? But what I'll do is I'll just find the total charge. And I know the charges will redistribute until V1 equal to V2. These two information is enough for me to form two separate equations and then merge them because total charge is Q1 plus Q2 by conservation of charge. Okay, if you want some similar questions to this, or rather this is a new one, but it was inspired by an old question. Older question. This is like a combination of Winter 10 P41 question 4. If you're referring to my topicals, it is page 5. You do later lah. And a combination of, I think I've discussed this question before. If not, you should try it. May, June 2, 3, P42, question 5. This is page 31. Because effectively, right, what we're having here in this case is I have one capacitor, C1, which is the sphere one. This circuit. So maybe should I use the, I'm just going to use the same color, C1. And then I have another capacitor here, C2. But right now, C1 has all the charge and C2 got no charge. The switch is open. Then for this one, your C1 and C2 has closed. So they will redistribute the charge. Maybe something like this. C1, C2. So in place of a capacitor, we are basically putting a metal sphere, which to be honest can be treated as a capacitor, two capacitor in series. Another similar one would be Winter 11 P43, question 4. They are similar, but it requires a bit of thinking. Okay. Especially this one, the latest one. Okay, moving on. Dun, dun. Step 6. And 18. Okay, this is Winter 18, paper 4. The focus is on part C, but I'll run through the whole question with you in case you haven't done it yet. Okay. So the first part is a pretty standard explanation. This is an old question. Okay. So gravitational field strength is basically gravitational force per unit mass. Don't write the equation, okay? This is the definition. So the second part, explain why at the surface, gravitational field strength is equal to acceleration of free fall. Well, from the definition, gravitational field strength. I don't know, this is a very strange question because I don't really know what they're asking. G is force per unit mass. From Newton's second law, especially if your mass is constant, F is equal to ma. So A is also equal to F over m. So hence G equal to A. Okay, that's all. Okay, part B, there's an isolated uniform sphere with a radius r. You're asked to sketch from R to 4R. This one is, when I see this kind of graph, I'm very happy one because it's a very nice bonus 3 marks. At R, it is 1G. So G is inversely proportional to R squared. From this equation, Gm over R squared, where R is the distance from the center of the planet. Okay. So this means if I double the radius, I 1 over 2 square the gravity. And then this is 1 over 3 square, which is 0.11. 111. No, wait, 1 over 0.11. 4 would be. So just for context, this is G. This is G over 2 square, which is 0.25 G. G over 3 square will be 0.11 G. Then at this point, G over 4 square would be 1 over 16, 0.0625. So please plot accurately. Yeah. This is 2.5 boxes. So this will be 2.5. And 0.11 divided by 0.025, 4.4 boxes. So 4.5 boxes here. 3 marks. So with a smooth curve, it's a 1 over R square graph, right? Make sure you pass all the important coordinates. 3R and 4R in a reasonable looking shape. Something like this. Let me make this darker, thicker. Okay, 3 marks. If they want you to draw inside the planet surface, this question is not required, has not required you to. It looks like this. Straight line passing through the origin. You can refer to the, I think, Winter 2-3 paper 4. Not sure whether it's 4.1 or 4.2 lah. They got this graph one. Okay, moving on. The planet in B has a radius of this much and a mean density of that much. So density is mass over volume, which is mass over 4/3 pi r cubed. Calculate the acceleration of free fall at a height r above the surface. So acceleration of free fall is equal to g, because F equal to ma, and the force is mg is ma. So it's m. In case you don't know what m we're talking about, this is my planet, capital M. We are measuring the radius r from the center. Oh, but it's r above the surface. Okay. So r above the surface. Tiny mass here is m. The force acting on this mass would be mg. But mg equal to ma. So basically we're looking for g lah, okay? And also the question sort of like asks you to explain or think about it here already. Find g lor. So got equation. Gm over a height r above the surface, okay? But what is capital R? Capital R is the radius. So the total height measured from the center is not R. It is R plus R squared. Okay, we always measure distances from the center to the object, making this 2R. Okay, and then you think to yourself, teacher, I don't know why it's R. I don't know why it's M. Don't worry, you have the density. And you also have R lah, this value. Okay, so let me rearrange my equation a bit. This will be Gm over 4R squared. But also at the same time on the side, I know density is mass over 4/3 pi r cubed. So I can substitute mass inside what? It'll be 4/3 pi r cubed times density, which I will do so in this equation. A is G, 4/3 pi r cubed times density divided by 4 r squared. Let the chopping begin. So I am not in a rush to substitute one. I only substitute when I'm fairly sure that I can put stuff into the calculator and get something. If I start substituting my R in the beginning, like the second line, I'm going to realize that I don't know M, but I still have to keep copying this 3.4 times 10 to the power 3 at the 1. So a good habit is to substitute later lah. But all these are small, small things. They're not too big of a problem if you can solve the question. So I'll cancel everything. And eventually, I'll have A is equal to G pi R rho over 3. Because got 1/3 there. They'll put pi over 3 here. Okay. 6.67 times 10 to the power -11 pi over 3. 3.4 times 10 to the power 3 times 10 to the power 3 because of the kilo here. And the density that we have is 4.0 times 10 to the power of 3. Yeah. Then you have your A is 0.95 meter per second square. Stay calm. Can do one. So as usual, we don't know what we will see in the question, but you got to trust that the question has enough for you to solve it. So step by step, try to write down relationships that you can think about, stare at them, and see how to bring them together. Okay, the next request It's question 12. Is there a question 12? There is. In part 3. There has to be a reason why it keeps jumping back here, right? OneNote things. Okay. This one also very deja. But never mind. I think I've answered the first few parts already in the class discussion. Maybe not with your class, but doesn't matter. We will balance all the equation that we see as a reflex reaction from many years of chemistry training. Maybe it's just me. So if I see 1, 0, I already know this is the beautiful neutron. Okay. And then this is the data of some binding energy per nucleon. Okay. So normally in the exam, if I see important things like this, I will circle with pencil one. If I got time, I come back and erase. If not, it stays like that. I don't really care. Okay. Part number 1, state the binding energy per nucleon of X. Because the last thing I want to do is to leave a prefix inside the table and forgotten to transfer it into my calculation. This will be 0 joule. Neutron, proton, electron, all that don't have binding energy because it is not part of a nucleus. 0. Calculate the energy change that takes place in this reaction. Another way of saying that this is energy released. So we can take the binding energy of the reactant, subtract the binding energy of the product. Binding energy of the reactant. Reactant would be helium. 11.329. Our times the 10 to the power negative 13 here. Okay, so 11.329. This is per nucleon, so it needs to multiply by 4. Product minus reactant, like that. Final, which is the product. Okay. My reactant would be deuterium, 1.7813 times 2, because the nuclear number is 2, plus 4.5285 times 3. And this whole thing, we would multiply by 10 to the power of negative 13. It will get 2.82 times 10 to the power of negative 12. As usual, if can, write extra significant figures lah. This one got 5 significant figure. We don't expect you to write 5, but 4 would be nice. 3 also would be nice. Definitely not 2. Okay. So my reaction was tritium and deuterium makes a more stable helium, inert gas, plus a neutron. This is the reactant. This is the product. And you minus or you get a positive number, showing me that it is more stable. Or you know chemistry. Helium is an inert noble gas. All right, so just a heads up. Remember, energy change can be delta mc square, can be mass defect, can be binding energy difference. All right. Using this answer, determine the energy release when 2 grams of deuterium reacts with 3 grams of tritium. Hang on, let me yoink this one first. So those of you who do chemistry, this is an easy question now. But if you don't do chemistry, maybe some help understanding for you. This 3 gram is commonly known as molar mass, meaning 3 gram of tritium is equivalent to 1 mole of particles. Likewise, this 2 here is also the molar mass. So meaning 2 gram of deuterium is equivalent to 1 mole of the particle. 6.02 times 10 to the power 23. Okay. So this means because I got 3 grams of tritium and 2 grams of deuterium, this shows me that there is 1 mole of reaction occurring. So hence, the total energy will be equal to the Avogadro constant, the number of particles for 1 mole, which is Na, number of particles of 1 mole, this one also Na, multiplied by your 2.82 times 10 to the power negative 12. So 6.02 times 10 to the power 23, 2.82 times 10 to the power negative 12, you'll get 1.7. 1.7. 1.697, okay lah, 1.70 lah. Times 10 to the power of 12 joule. Lots of energy. Few gram of particles, lots of energy. That's why the sun is such a large nuclear reactor. Okay, so that's all the question I have from Amber. When it comes to particle physics, right, whether it's gases or nuclear reaction, those are the places where you normally encounter the mole concept or Avogadro number. Okay, basically when we generalize the energy calculation or the root mean square calculation or the kinetic calculation beyond one particle, beyond one reaction. So a little bit of basics would be helpful. Okay, I'm going to take a 10-minute talking break where I gather the next person's questions. You can feel free to send yours if you have any, or go walk around a bit and stretch your legs. We will come back in 10. Pause the recording. Recording in progress. Okay, let's resume. These questions are all small questions. I won't attempt to answer the whole thing. Because it's just basically the answering technique lah. Okay. So this one is from a pretty old past year question, 2018. Yes, 2018 is old. This is ON 18. Check the year. ON 18 P42. I think it is also in the, you can find this on the channel. But what we want to care about is explain why when I turn on this current is turned on here. Okay. It doesn't affect the current in the sections PQ and RS doesn't affect the balance of the wire. Okay. My answer is wire is parallel to the field, so no force. So let me ask you a question. My magnetic pole piece, the magnetic field is like this. Either, let's say this is north, this is south. Or it could also be, this is south, this is north. Either way, it doesn't matter lah. It has to be in this plane. Parallel meh? Which part parallel? So the answer is no. Your statement is wrong already. B and I is not parallel. This 2.7 ampere will go like this. Okay, this one will go like this. QR also not parallel. QR is also perpendicular. No body is parallel in this case. Because if I draw a view from here, let's say I put my eye here, okay, what I see is this magnetic pole, and then let's say the magnetic field is going into the paper. Then my coil or my turns or wire look like that. This is SR. Down here, Q, and this is P. No body is parallel to B. Okay or not? This part settle first. So you have to have a proper perspective of the 3D drawing based on whatever they give you. They can give you anything one. So if drawing in 3D is troublesome, you can always view from 2D. Now, if I view from 2D and I want to draw the direction of the force, FBI, B is going inside, and my current is pointing downward, the force is here. Here, the current is pointing outward, the force is here. These two forces are equal magnitude and opposite direction, right? And because they are horizontal to the pivot, imagine your force is here. Your force is here. Equal magnitude, opposite direction, they cancel out anyway. And also at the same time, the pivot is also in this same plane. You can see, same direction. So if I view from this side, the pivot is like here at the back, towards the back. And then if I want to draw the forces for QR, the force will be here. So from the perspective of QR, the only force that will cause moment is this FB. Okay, so this is view 1. View 2 will be more suitable if, let's say, you struggle again, braining the 2D, the 3D, I mean. View 2 means I view from here. If I view from here, I see a pivot, I see one wire, and then I see a wire drop down this way. This is my SR. That's all I see, if I view from this side. So if the force acting on QR acting downward, this FB is acting here. So this will cause a rotation in this direction because the pivot is here. And then I hang a hair or a small mass here. This small mass will cause another rotation in this direction, clockwise equal counterclockwise. Okay. Let me know if you have any follow-up question, Glenn. You don't need to know the direction of B. There are only two possible directions. You can choose one. Either way, the forces will cancel out, and also they are parallel to the pivot. So there's no moment of forces. Any follow-up questions regarding this? Okay. This one, I assume, is rounding error, so it doesn't matter. Let's say they ask you to calculate here and you put 1.7. Normally, in this kind of calculation, my only recommendation to you is show substitution. I will minus 1, mark 1. I don't see substitution. What is this and what is this? Okay, like you're looking for M. What is this and what is this? So immediately here, I minus 1 already. Okay. Assuming you put in the substitution, it doesn't matter because whether you put 1.7 or what was it again that you typed just now? Whether you put 1.7 or whatever, it doesn't matter because you need to show your substitution one. Okay. Gotta, I mean, I don't know if that makes sense. Let me know. Because I felt like I've explained this to you many times before, right? This is 1.667. Up to you lah, it doesn't matter. Show substitution. My recommendation is substitute 1.67 here. It's not weird, Glenn, like I've mentioned just now here. This part, where was it? Not this one. I've mentioned it before. Here. You see this 2.766 that I've calculated? I want my final answer to be 3 SF. So whenever I substitute, it should be 3 plus 1 SF for better accuracy. That is the recommendation in the examiner report. Okay. They are not always very strict about this. It's always just a recommendation. But sometimes they are strict about it and sometimes they will deduct your mark. But maybe 1 mark here and 1 mark there, lor. Maybe the whole paper 2 to 3 marks. So if for me as a student, I don't like it when they deduct my marks lah, because this marks shouldn't be deducted one. Correct? So I will put extra lah. Put extra probably won't deduct. So it should be at least 1.67. It's not even wrong if you put 1.66666667. You know what? If I'm you, I would just put 0.2 over 0.12. I want the accuracy lah. But the more important thing for you is please show your substitution. If you don't show substitution, it's auto minus mark already, regardless of what your final answer is. But generally speaking, if you want your final answer in 2 SF, this should be 2 plus 1 SF. Okay. I don't know what is the question here. You just measure lor. This is the graph that we've sketched just now. You want to measure 235. So 235 is probably somewhere here lah. You mark here lah, somewhere here, 235. If 235 is here, I'm sure you can roughly figure out where 95 and 139 is, because the peak here is 35. Sorry, not 35, 56. So you use your ruler to measure lor. I know what the mark scheme ones are, which is roughly somewhere like that. Okay. No. Just measure, just use ratio lah. Where are you going to mark? Where are you going to mark 95? And where are you going to roughly mark 139? You use your ruler to measure lah, roughly lah. It's just 1 mark. It has something to do with the peak because the peak is 56. If here is 56 and here is 0, you should be able to ratio your way to the other things already by by roughly estimating the distance. So actually 95 should be closer lor. Because 95 to 56 is 40 ma. But 0 to 56 is 56 ma. So somewhere here. So it should be 95. And 139 should be somewhere in the middle. 39 somewhere here. 235, something like that. They are not very strict about this one. Just make sure it's not too out of the way. The astrophysics answers I have uploaded today. So you refer to that one lah. All the astrophysics questions. Especially the ones that are not from Cambridge, not from CIE, not from Cambridge A-level program. I took questions from Cambridge Pre-U program. Cambridge Pre-U. You are taking Cambridge A-levels. Not the same thing, ah. But don't worry lah, they cancel the Pre-U and they make the A-level harder. That's your situation right now. They have cancelled the Pre-U to make A-levels harder. Okay. Winter 2, 3. April 4. Jan. Okay. Hang on. No one in Malaysia is allowed to take the pre-U. It's only offered in certain elite schools in UK. Elite schools. Because the content is harder. So I'm guessing that they probably find it harder and harder to execute because it may not be that straightforward in looking for good enough teachers to teach difficult content. Maybe the elite schools don't want to answer anymore. I don't know. But yeah, they offer to only to certain schools in UK. Only UK. It's not Cambridge International Assessment. No, no. CIE ma, Cambridge International. No, no. That one is just UK one. And only certain schools. Nah, those are very fancy school lah. Everybody wear uniform one. School like few hundred years old one. That kind of school lor. Don't worry, don't feel bad. It's just a school. Still some stuff. Okay, so this one is from, but we can use their question lah, because I want to learn from them, especially when something is new in the syllabus and I don't have the questions. So I use their questions. Okay, so this one, the definition of the radian, you use S equal R theta. If S is equal to R, theta will be equal to 1. So S equal to R, meaning if you have a circle, this is R, this is S, they are the same length. This angle is 1 radian. So it is the angle subtended at the center of a circle where the arc length is equal to its radius. Write full sentence, okay? Just because the mark scheme did not write full sentence doesn't mean you're allowed to not write full sentence. Mark scheme is for the reference of the examiner, not for you to copy the answer. So it's to refer the important points, not to reproduce the mark scheme. Okay, so here we have a minute hand revolve at a constant angular speed. The minute hand or 1 revolution is 60 minutes on the clock lah. Okay, so completing 1 revolution every hour. A small piece of clay is attached to the hand with a center of gravity a distance L from the fixed end. Okay, so we stick a little bit of clay here and it's going to rotate. Okay, fine. Calculate the angular speed of the minute hand. Omega, you can use 2 pi over t. 1 cycle, right? So this will be 2 pi over 60 minutes, 1 per second, 60 seconds. So 1.7 times 10 to the power negative 3. 2SF is good enough, although they didn't provide any other data, but it's fine. You want to write 3 also can? During the time interval of 1,400 seconds, the center of gravity moved through a total distance of 0.44 meter. Okay. Calculate the angle through which the minute hand has moved in this time interval. So if you think about your minute hand, there's a piece of clay here, right? As the minute hand rotate, the clay will rotate. So this is the distance d. So I can use S is equal to R theta, where S is the distance traveled, 0.44. I want to find the angle, theta, in radian, so that's great. The distance of the modeling clay. Oh, we don't have this R. In fact, we need to find this R. Okay. So can't work here because we don't have the radius or the distance of the modeling clay. But we do have this value here. Right? I have this much more per second. Okay. omega is theta times t, or theta over t. So 1.7 times 10 to the power negative 3, theta over 1400. Okay. So from here, you have your angle theta, which would be 2.4 radian. And I can take this with me to this part, determine L. Theta is 2.4, so L would be 0.18. This is also the radius of the circle formed by the clay. Calculate the magnitude of centripetal acceleration. AC is r omega square. I use this mainly because I have the value of omega already. Always show the substitution. Wait, I got omega. Omega is 1.7 times 10 to the power negative 3 square. So this one, if let's say you want to put more SF, it is recommended. So normally what I'll do if I'm writing the answer, let me calculate this. This is 1.745 times 10 to the power negative 3. So if I want to write this thing in 2SF, I should at least write 1.75. But 1.75 looks very different than 1.745 lah. So they put the whole thing long. In this case, I don't really think it matters. But if you care deeply about this, here's what I'll write. Up here, 2 pi over 3600. This is the most accurate one. Okay. So this will arrive you at 5.5. Okay. Last part, using this calculation, explain why the variation with time of the magnitude exerted by the minute hand on the piece of modeling clay is negligible as the minute hand undergoes one full revolution. Well, this one is because your centripetal acceleration is very small. Centripetal force will be equal to the force, the normal force exerted on the minute hand, exerted on the clay. So the reason why the clay can stay here is probably there's some sticky normal force, sticky electrostatic forces, okay, sticking it to the minute hand. And that forces, that normal contact force actually provides your centripetal force. It's like a form of friction. So the friction between the hand and the clay, the minute hand, the clay is the one that causes or rather contributes to your centripetal force. Okay. And the weight, so if you think about this is your minute hand, this is your clay. Your clay is about to travel here. The center of the circle is here. There is also mg. And then there's this force exerted on the clay. I don't even know which direction it is. It depends on what is needed. So maybe I plus mg. Okay. So this one would be MAC. This is force exerted on the clay. Because this AC is very small, compared to G. Okay. So if it's very small compared to G, it really means that it is negligible. Maybe it'll be easier for you to visualize if we think about the forces. Let me think. If you are circling, the weight is pulling you down. So to prevent you from going down, there has to be a stickiness or a normal or a force exerted on the clay. What do I want to call this? F. I want to put FC, but that is centripetal force. So F exerted on the clay. FEC? Anything lah. Okay. Because if it's just the clay on its own, the weight will pull the clay down. The clay will slide down. No? But obviously there's another force exerted on the clay by the minute hand. But the center of the rotation is here. And your centripetal force is here. So based on this more accurate drawing, although to be honest, they are the same drawing. The center of rotation is here. I'll take one circle for you. Center of rotation is here. So net force is equal to centripetal force. Mg minus FEC is equal to centripetal force. Something like this. Okay lah, we write down lah. 2 marks only, don't think too much. Okay. So centripetal acceleration is very small or almost negligible compared to the acceleration of free fall. Hence, the resultant force is, the variation is negligible. Hence, the variation of resultant force is negligible. It's a little bit like they're actually not asking your resultant force. They are asking this one. Variation with time, the magnitude of the force exerted by the minute hand. So they're basically asking you to think about the whole circle. Because this is at the top of the circle. I put this one here. This is the top of the circle. Right? Your force exerted, this one, is equal to mg minus fc. But this AC is very small. Let's compare to the bottom of the circle. Your minute hand is like this. If you compare to the bottom of the circle, weight is still acting downwards, right? But the other force is in this direction. And your resultant force is here. So for this, net force is equal to centripetal force. The centripetal force minus mg is equal to, the force exerted on the clay minus mg is equal to Fc. So from here, force exerted on the clay is equal to Fc plus mg. Or to compare with the other one, mg plus Fc, which is mg plus mac. So they're asking why is this variation negligible? Why is the FEC on top more or less equal to the FEC at the bottom? Well, this is because this is very small. This is very small compared to mg. So the variation of resultant force, or rather the variation of centripetal, not centripetal force, this one is negligible. I guess a sentence that would make more sense to link these two centripetal acceleration very small compared to the acceleration of free fall, since the direction of force, they call it, exerted by the minute hand on the clay is opposite to the direction of force of gravity or direction of weight of the clay. The very okay, the changes to the resultant force is very small because your centripetal acceleration is much more smaller than g. Something like this. That one is just a keyword, so we can. So this one is the kind of marks where this is for the good students to score lah. Okay, if you want to pinch a good mark or a good score for the paper. Okay, so again, if it's out of two, maybe you can't get 2 out of 2, but you definitely can get 1 out of 2 because use your answer ma. So I already calculated this one. This is acceleration. Definitely we are going to think about gravity. So I'll compare it with gravity. Okay. And then maybe you will need some time drawing this to convince yourself. Why is it that at the top and at the bottom, the force exerted by the clay by the minute hand on the clay is not changing? It's not that there is no force. There is force, but the force is negligible. Not negligible. The variation of it is negligible because your MAC is very small. That final mark lah. Normally, there will be I think there will be about 5 to 8 marks that are very hard to get, like this one, because they say variation ma. So actually what I'm doing is I'm comparing this versus this. So I'm basically arguing that because AC is very small, it doesn't matter whether I subtract or I plus. The variation is very small. That's the answer. Okay. Let me know if you have any follow-up questions. Let's see if I've done the AC questions. Okay, so Glenn, I've already discussed this question in detail in class. which is basically telling you that this is the electron motion and you want to draw the AC graph. So down here is the electron motion. Think about the electron. Um, you need to think about the drift velocity as a derivation. So you derive law. I don't understand your question. It's just integration. I mean, differentiation. The mark scheme say positive. Correct. It's positive. The red color one. Okay. Direction of I is positive. Because when you differentiate, you get negative, but this is the drift velocity of electron. When you differentiate sign, you get negative sign, you get negative cos. But this is the drift velocity of electron. Direction of current is opposite to the direction of electron. So you need to add a different negative in front. This negative here is because I opposite direction to electron. Yeah, this one you think a lot. Only 2 marks. Those kind of question lah. A bit brain pain one. But the winter 23 papers are difficult lah. Across the board. So you ask me whether there's any strange question. I think the winter 23 is strange enough lah. No need to do any other strange questions already. Rest your brain so that you can. So you are okay on Monday. In fact, on Sunday, I'll sleep early. Let my brain relax a bit first. Unless you have a lot of things you haven't studied yet lah. But regardless, still sleep early. You need a flexible brain. No flexible brain, how to brain things.
Is Feb March 24 weird?
Sorry, what?
Is Feb March 24 as weird as winter 23?
No. Sometimes they overset too difficult and then they look at the candidate's mark, then they go like, oh, well, I think we set too difficult, then they set a bit easier. I don't think 2-4 is as hard as winter 2-3. Still 8. I don't really understand what you mean by there has to be a carrier. Because the question is basically asking you to justify or explain the existence of your threshold frequency. So what are we carrying? Okay, so this one, generally speaking, this is okay. Each electron can only absorb 1 packet of electromagnetic radiation or 1 packet of energy. So I will write this. And then I will say, since the energy of each wave packet is proportional to frequency, if the energy of 1 packet is not enough or insufficient to escape metal surface, there will be no photoelectric effect. So the observation of photon is actually this one. This one already tell me that this is photon already. But you want to complete the story, lor. So electron will be emitted if the energy of one packet is enough. Why one packet? Because each electron only take one packet. Why a specific particular frequency? Because the energy of the packet is proportional to frequency. There is no carrier one. The light particle has no mass. So it is just a burst of energy that is discrete. That's all. You can visualize them as a ball of energy, but it's pure energy, nothing else. That is a photon, pure energy, nothing else. Well, no need to mention the carrier. Intensity of radiation means I create more packets. So in short, if you want to brain it properly, I guess you could say that for photoelectrons to escape the metal surface, each electron will absorb all the energy in a single packet known as the photon. Since the energy of the photons is dependent or proportional to the frequency, to its frequency, and increasing or changing its intensity only increases the number of photons and not the energy inside a single photon. There exists a minimum frequency corresponding to the minimum energy needed for electron to escape or to leave the metal surface. Better? This one got more than 3 marks already, but maximum you can get is 3 lah. Each electron, that means one electron, one packet, 1 mark. So then energy of a photon, proportional to frequency, 1 mark. Increasing the intensity only increases the number of photon, 1 mark. So there has to be a minimum frequency corresponding to the minimum energy needed to the energy metal surface. We can continue one, but I scared no space only. If the electron and it does not receive enough energy, it will not escape the metal surface. It's good enough. You don't get... Okay, what is the definition of a photon? Define photon for me. What is a photon? discrete packet of energy. Yeah, lor. So the first point already described the photon already. No, the first point has already described the photon. If it's not discrete, it means that, let's say I don't have large enough frequency, but never mind lah. I just spam the electron with many, many photon, then the electron will gather all the energy, and then eventually the energy will leave. I mean, the electron will leave because eventually it will gather enough energy. But that implies that the energy is not discrete, that the energy is continuous. So it's not the last sentence that link to the existence of the photon. It is the first sentence. The fact that there is a minimum frequency. It's a bit like you cannot just sit your paper for 10 times and gather your marks. Cannot be. So this shows me, just the fact that you cannot do this already shows me the existence of a discrete mark for your paper, where the marks may not be combined. Although that would be a nice thing. So one electron absorb energy in one single wave packet. This is already the photon. But of course, you write the first sentence is not enough lah. You need to link back to the question. Okay. So provide more description. How does this show you that the photon, we are no longer talking about the fact that photon exists. We are now talking about why does this minimum frequency, threshold frequency, tell us that there is a photon? How I know? Why is this frequency important? So the first thing I would think to write about is, since I already explained the existence of a photon, I will link it to the threshold frequency, because I want to link it to the minimum value. Okay, sorry, I cannot memorize one. They can ask you to justify and explain from many different angles. So in short, the existence of photon is proved because each electron can only receive one photon. And when the electron receives energy, if the frequency is not enough, the electron cannot escape, since the energy of the photon is dependent on frequency. So since one electron, one photon, one minimum frequency. All right, take some time to think about it lah. Wait, let me try to find the question. This one used the mole concept, probably using the mole concept. Crop the question. Let me try to understand your question. Okay, this is a fission reaction. These two are beta emitters. Sure. So this is not the end of the decay lah, right? Barium has a half-life of 18 minutes. Decay constant is 6.4 times 10 to the power -4 probability of decay in 1 second. Half-life of krypton is very short, 3 seconds. A mass of 1.2 gram of uranium-235 undergo this nuclear reaction in a very short time, a few nanoseconds. So that means all the uranium-235 has already decayed. All uranium-235 already decayed. Very short time, ma. Some more, they even tell you reaction has been completed or confirmed already. Now 12 time already, reaction already decayed. So hence, I can find the number of particles of U235 at 1.2 gram divided by the molar mass 235 gram multiplied by the Avogadro number. Or you can take 1.2 times 10 to the power negative 3 kg divided by 235 times 1.66 times 10 to the power negative 27 kg. So the first one is my preferred way because I like to use the mole concept because I'm fluent in chemistry, at least fluent enough or more familiar to me. Or I could do this. This is fine too. 2 and 3. It's 3.076 times 10 to the power 1. The answer will not be exactly the same one because they're just different ways of estimating the number of particles. Whichever works, they are both okay. So 1 uranium-235 will create 1 barium. Since all of the uranium-235 has decayed, this is also equal to the number of barium. Is that okay? The reaction has completed. There is no more uranium-235 and only barium remains. This is also equal to the number of kryptons, correct? That's why this is a chemical reaction. I mean, it's a nuclear reaction, which is also a chemical reaction. Although I'm not quite sure whether they are the same. So the number of particles, you start with 3.07 times 10 to the power 21. Uranium-235 eventually will drop to 0. Few nanoseconds there. So fast. Maybe I draw shorter. Then immediately barium will be here. Not just barium lah, krypton will also be here. Same amount. Conserve all of it reacted. That is conservation already. What? The total number of particles will still be the same. Not total number of particles. The total nucleon and proton number will still be the same. Okay, the next part, you are going to calculate the total activity of barium-141 and krypton-92 1 hour after the fission reaction has taken place. 1 hour. I can ignore the 3-second one already. I mean, I can include it. Okay, never mind. Activity of barium plus activity of krypton. This will be A0 E negative lambda T for barium plus A0 E negative lambda T for krypton. Guess what? A0 is lambda N naught. So lambda N naught E negative lambda T for barium plus lambda N naught E negative lambda T for krypton. It's doing maths law. I have the half-life of barium, not half-life, I have the lambda for barium. 6.4 times 10 to the power negative 4. I got the N naught, 3.07 times 10 to the power 21. E negative 6.4 times 10 to the power negative 4. This one is in seconds. So I should use time in seconds. 1 hour would be 3600 seconds. My hunch tell me that krypton will be very small, maybe even negligible. So in order to test this hunch, I should separate out krypton and barium separately. So ln 2 over half-life, 3 seconds, times 3.07 times 10 to the power 21, e to the power of negative, ln 2 over 3 times 3600 seconds. Okay, press calculate the time. Hang on. Let me give the people the question. 3.07, 21. Hopefully I'm pressing correctly. 962 times 10 to the power 17 plus this is 0. You can try and press and see. I got 0. Yep. Hello. How I know it's 0? Because your half-life is 3 seconds. After 3,600 seconds, it is unlikely that you have anything left behind. But this is how it looks like if you want to calculate. If not, I would just justify here that the A for krypton will be approximately 0, if not equal, since its half-life is 3 seconds and the activity is 1 hour later. Can 18 minutes are very different because 18 minutes is about 1/3 of an hour. Hmm. And here's another quick comment about a question that can look like this. Normally, nuclear physics, if it's a standalone, the question is quite a short one. So spontaneous, random, standard, make sure you know how to write them down. This one, you want to calculate the decay constant. Decay constant is only dependent on half-life. Half-life dependent on the type of sample. So my response to you, Glenn, is half-life doesn't change one because the decay constant is a constant. Okay, anyway, this is your activity. You want to calculate lambda. You have this sample here. Okay. So we're going to use A is equal to lambda n. But first I need to calculate the number of sample. So n will be the mass, 1.0 times 10 to the power -9 divided by strontium 90, 1.66 times 10 to the power -27 kg. kg. Okay, then you put everything inside. 5.2 mega. Mega is 6. Lambda. After you announce your equation, at least spend a line to show the calculation. Seven. Okay. This chapter is very maths one. So it says here that the activity of the sample after one half-life is found to be greater. If the activity is greater, it's not because the detector didn't catch it lah. This is probably because the product of the decay is radioactive. So we haven't finished decaying yet, still have a product. Activity and the count rate is the same thing. It means the same thing. Because you are counting how many activity in 1 second. So this 2.6 megabecquerel means 2.6 times 10 to the power of 6 count of decay per second. The detector reading is never accurate one. If the detector is too far away, sometimes it doesn't pick up the detection. Sometimes you take out several detection at the same time. You can watch the recording. I talked about this already one. So activity is a theoretical calculation, but it can be seen as equal to the count rate. Okay. It's a bit like length, and the length that you measure with the ruler may not exactly be the same, because the detector is an instrument. Instrument is imperfect. There is no perfect instrument in science. Okay. Okay, I'm towards the end of Glenn's question already. If you have any other questions that I haven't addressed yet, can feel poke me. I think Amber wanted me to talk about the resultant field, which I can. In a sec. It'll be after these two questions. Okay. I'm assuming you're talking about the X-ray spectrum graph. I don't think it's in the syllabus anymore lah. I don't think much of it is in the syllabus anymore. But let me quickly explain to you, and you tell me where you don't understand. You can find this inside your written notes, okay? Your written notes is, if you go to the Cal resource folder, somehow a lot of people don't know this. You go to the written notes, you see it's A2 written notes, 2022 syllabus. Everything is here already. I click for you lah, including the Cambridge pre-U answers that you asked for chapter 25. Everything is here. Yeah, hang on. Let me put the link again for you. You all don't have the habit of clicking around. Why not? It's an entire resource folder. Why don't you click around? I can't be pasting everything inside the chat, right? That'll be very weird. So everything is inside the Cal resource folder, Google Drive resource. Here. Click on this one. This one. We should bring you to here. Oops. This one. We should bring you to here. Then you can go to written notes. Then it would be here. Okay. Anyway, this one takes a while to load lah. So anyway, that is why I want to point this out to you, where you can find what I'm about to show you. So this one, by the way, is the syllabus, the new syllabus. It doesn't look like they want you to talk about the spectrum. I just leave it inside the notes only. Okay. Let me see if I can understand your question. When the energy of X-ray is maximum, the intensity is close to zero, meaning there is very, very few photons. Okay, so I don't know what is your working model with this, but maybe you ask me follow-up question. Okay, so when the electron collide with the heavy target metal, the electrons generally will be slowed down like this. Okay, the fast electron go close to the nucleus of the heavy metal. When the electron passes near the nucleus, it is slowed and the part is deflected. It's slowed. So around 80% of the X-ray is photon. So it's not like I have 100 joule of energy, 80 joule become X-ray. No, 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 no. I have 100 photon, 80 photon become X-ray. These are discrete packet of energy. Okay. So the more intensity means more number of photons. And why do I get photon? Because the electrons slow down, the kinetic energy converts to X-ray. So because the electrons slow down at different rates, some of them slow down more, some of them slow down less, they will lose different kinetic energy. The one that loses the most kinetic energy will create the X-ray photon that has the most energy. Okay. Third one is about the spectral lines. For you to get that little peak, this peak here, this is because your high energy electron will whack inside inner shell, some inner orbital electron. Let's say knock away this orange electron. Oh, orange electron leave away already. Suddenly the electron at the higher energy level go like, wait a minute, there's an electron space down here. There's an open space. So this green color electron will look at the more stable open space and go to the lower energy level. But when you go to the lower energy level, in order to conserve energy, you must give out photon emission spectrum. So I will give out an X-ray photon due to the orbital transition. We all know this orbital transition is discrete. So the X-ray photon must be discrete. You will get these discrete lines. Let me know if you have any follow-up questions. So the intensity is basically the number of X-ray photons. Why most energy is intensity 0? The intensity, okay, like this. Let's say I throw 100 electron. Okay? 100 electron. 10 electron will slow down a little bit. So the wavelength of the photon is very long. Do we understand the connection or not between these two? Do you understand what is intensity? Intensity is linked to the number of X-ray photons. Okay? So How should I explain this? Because I feel like your question means you totally don't understand what is going on. Is it like probability? Yes, it is probability. It's a distribution. It's literally a distribution. Like that, lor. So you don't want to write intensity, the number of electron or number of photons. And intensity is number of photon times energy of one photon per unit area or per unit time. Assuming that the area of the heavy metal is constant, the time frame we are taken is constant, then the intensity is proportional to n at any given lambda. Okay, meaning at any fixed value of lambda, the greater the number of photon, the greater the intensity. Okay. So maybe I got 100 electron, then I have 100 X-ray photon. So maybe this is 5, 10, 20. My scale got problem. 15? Okay or not? So for that single photon here, this one, at this point, because you can't really measure this 0.1. In the lab, we'll probably have something like this. So you extrapolate following the curvature at this point, all the Ke become energy of X-ray photon. Okay, let me know if you have follow-up question. I go and get a bottle of water. Here's my bottle. Hang on. Absolute zero is negative 273.15. No more already. Just negative 273.15. Because they use the phrase absolute zero. That's all. When you're converting, you will follow the precision of the question, but you're not converting now. You are stating what is absolute zero. Okay. No more request. Okay. Here is the electric field of one charge. Okay. So I think Amber is asking about this. So to understand the resultant of two charges, you have to understand one charge, right? Inside the positive charge, the electric field is 0. Okay. Inside a negative charge, the electric field is 0. Outside, it will follow the inverse square law. So it looks like this. Right? Direction, positive, negative. Direction, positive, negative. Okay? So in short, what we're talking about is for E, we will reserve direction for positive and negative. For V, because it's a vector, for V, positive and negative depends on the polarity. For example, for a positive charge, the V is always greater than 0. because positive charge will always repel the positive test charge. You want to move a positive test charge from infinity to this point, you need to do work positive, like compressing a spring. Okay. Whereas if you want to bring a positive charge from infinity to a negative charge, this will be negative because it's attractive. So once you know the shape of the graph, we can put two things together. Okay. So for example, if I have a positive charge and I have a negative charge here, both of their electric field are pointing in the same direction. Positive charge, the electric field will point out. Negative charge, the electric field will point in. But in a way, they are both pointing towards the right. So this is the red graph for Q1. This is the blue graph for Q2. If I add these two graphs together, I'll get the purple graph. Okay. Does that make sense? Little bit of blue plus a lot of red becomes slightly higher purple. This one, the turning point will be somewhere here. Normally is where they intersect. Okay. You can use this graph to describe electric field. For example, the E decrease from here to here, force decrease, acceleration decrease. At this point, the force is minimum, the electric field is minimum. Then it will increase in the same direction because E is always positive. Okay. The relationship between E and V is E is equal to negative potential gradient. So if I check out the gradient of the purple graph, the gradient of the purple graph here is 0. So here my E is minimum because dV dx is 0 or dV dr is minimum. E is minimum because here the turning point. Does that make sense? So E is the gradient of this graph. Okay. So here the gradient is minimum. So here E is minimum. Strictly speaking, if this one feels a bit unfamiliar because you're not used to seeing this in mathematics, I can just sum up the graph one. This is V1. This is V2. V1 plus V2, because they have opposite polarity, surely there will be a point in the middle where they cancel. This canceling point feels very important, right? It is corresponding to the turning point. Okay. Or this gradient, the gradient underneath, will give me the E graph. So at this point here, at the inflection point, the curvature of the graph is like this one. So at this point, dV dr is minimum. dV dr is minimum. The electric field strength is minimum here. Okay. And then for this one, the reverse will happen. No? Meaning now I have two positive charge, and the same will apply to two negative charge as well. The same, you can try out the same analysis. If the charges are both the same polarity, if you look at the field between them, they will be in opposite direction. Because E1 will want to go outwards, E2 will also want to go outwards. But if they both want to go outwards, this means E2 is negative because it's to the left. So surely there will be a point where they cancel one, where the resultant is 0. Sometimes they will ask you how you know whether same polarity or not. Here's the explanation. Okay. Then you can do the math. There are past year questions like this. But once again, I can use gradient. So at this point here, dV dr is 0, so E is 0. There here. I'm also summing up both graphs. So just adding the graph together. I think if you go back, or rather on your own, take a piece of paper and try to brain the field between these two settings while referring to these notes should be enough. And then go and poke one or two past year questions. I'm pretty sure I have already discussed with you before also. Okay, a few remaining questions for Feb March 24, paper 4. There's a request to explain this one. Okay. If half wave rectified, okay, so in case you haven't do the question yet, this is your full wave rectification and it's smooth with the capacitor. So you get this shape. Okay. It says that now the sinusoidal power supply has a maximum power of 16. So P max here is 16. State the value of the mean power when the output power supply is full wave rectified. So if it's full wave rectified, right, it really doesn't matter. Let me draw for you. This is your, let's say it's a sine graph now, okay? Is it a sine? Do they give me any information? Well, it looks like a sine based on the rectification graph. Okay, so this is your curve. Then if you want to draw your power graph will look like this. Right? This is your power graph. This is unrectified. If it's full wave rectified, how will my graph look like? IT. It will look like this, no? Like this, like this, like this, like this. Correct? But my PT graph will still look the same. Does that make sense? My PT graph will still look the same. Like this, like this, like this, like this, like this. Because the peak is still the same. Let's say this is I naught. This is I naught square R. This is still I naught. This is still I naught square R. So it doesn't matter. I just need to find the mean power, which is the maximum power divided by 2, which is 8. Mean power is maximum power divided by 2. Here's the derivation of y. It's only 1 mark, so it doesn't matter how you arrive at it. But if you want to know, here's the derivation. I guess you could reverse and go and calculate the root mean square and then come back again, but that one feels like a lot of work. Okay. So keep in mind this identity. Remember to write your answer in 2SF. Then for half wave rectification, instead of having this pattern, I will only have half a wave, meaning my PT graph will look like this, then nothing, look like this, then nothing. So I only have power half of the time. Then divide by 2 lor. So this one is 8 divided by 2 because I only have power half of the time interval. Is that okay, Amber? When there's power, it's identical, I naught. So this will still be I naught squared. Won't the power be constant? But there's no current. Why would there be power? There's no current flowing in my circuit because in half wave rectification, I block the current. So if there's no current flowing in my circuit, there should not be any power output in the resistor. That's my resistor now there. So it's constant, but constantly zero. Power is not constant. I mean, it's zero. When the current is flowing, instead of a curve, shouldn't the power just be constant? But the current is not constant. How can the power be constant? If my current is like this, surely my power is not going to look like this, right? Or this current is I equal to I naught sine omega t. Power is equal to I square R. I naught sine omega t square R. So it's I naught square R sine square omega t. So it should look like this. I mean, this. It's an alternating current, it's not constant, so the power should not be constant. Okay, moving on. Shouldn't the first change in EMF be half the magnitude of the second change? No, because the gradient is the same. The gradient of this blue line is the same as the gradient of this pink line. I mean, opposite sign, but same value. How do I know the gradient is the same? Well, two boxes, two boxes, two boxes, two boxes. Same gradient, no? Is that okay? Okay, so don't be fooled lah. Just because you draw a longer line doesn't mean that it's a bigger gradient. Go and try or redo if you already tried the summer 22. This one is a very exciting zigzag graph. The gradient a bit more spicy. But yeah, use the boxes to calculate the gradient. Normally you can use ratios. Okay, I think I have exhausted all the questions. Let me know if I missed out any of your questions, if you're still here. Think we have. I don't know why, but a lot of people got problem with this question. So I'll quickly run through this particular question. Wrong orientation. Hang on. It's not my intention. Okay, this one oh. Now let me read the question. Okay, so people want to know what is going on generally with the question. I'm not going to solve the question in the interest of time, but I want to describe what is going on to the coil. Okay. You know what? Because someone asked me this already, it'll be faster if I don't need to write. 1 second. Yoink. Oh, there we go. Okay. So this is the magnetic field. The magnetic field is changing. How do I know the magnetic field is changing? Because I have a graph. The graph tells me that B is getting bigger and bigger and bigger. What does the coil have to say about it? It does not like the change. It goes like, there is this cross magnetic field that is changing, I'm going to make my dot field to oppose the change. Everything is typed here already. Okay. In case you need another reminder of how these things tend to look like, there is a current inside the coil. Inside the coil, I can set up a magnetic field. This is a magnetic field that I see in blue color here. Okay. I stick the coil inside. When I increase the current in the coil, I increase the B in the coil. When I increase the B in the coil, I increase the flux in the green coil. And what does the green coil have to say about this? I do not like the increase in flux. I want to fight it, so it will make a dot flux. So EMF is induced in the square coil. The question can stop here, but unfortunately, we connect the terminals. And when we connect the terminals, we provide a pathway for the electrons to flow. That's why when the terminals are connected, current flows in the square coil. So now I have a square coil with current inside a magnetic field that is cross. Remember, you cannot interact with your own magnetic field, but you can interact with your neighbor. So then when you use Fleming's left hand, you will find that the forces on each side of the coil is force inwards one. So the coil is being squished. So due to the fact that there is induced current and this induced current exists inside the magnetic field, it experiences a magnetic force acting on opposite side of the coil like so, forcing it inwards. Depending on how flexible the coil is, the coil may change shape. Okay, but also because there's current in the coil, there will be electrical energy dissipated as heat due to the resistance of coil. Okay, so how you answer this really depends on what the question wants from you. This particular question is very open because it says here, explain the effect on the coil when connecting the terminals together during the change in magnetic flux density. So you just need to start the explanation here. You don't need to explain why there is EMF because you have already calculated the EMF previously. Because they did not ask you to explain the EMF. They say explain the effect of the terminal connected during the change in flux. At most, I will just briefly mention there's an EMF induced in coil, and because of this, there will be a current inside the coil. Two things will happen. The coil will experience a magnetic force. To find the magnetic force, right, according to Lenz's law, this is an opposition. So the magnetic force, you can either use your Fleming's left hand. You can also think about opposition. So in this situation, it's very hard for me to visualize how the opposition will look like because the coil is kind of stuck inside the magnetic field. It's not like it can experience a force in a meaningful way to yeet it or to kick it out of the coil. So you can think about Fleming's left hand, or you can think about how energy is lost as opposition. Okay. That's all for this part. Then Winter 23 P42 question 3. Okay, this will be the last question for the day. Anyway, if you need any screenshots from all of this, you just ping me. Use first law of thermodynamics to explain what happens to the internal energy. This is basically the question. So this one need to brain a bit one. You think a bit. As usual lah, or like all explanation question. Still gonna write a statement about delta U. Oh no, don't talk about delta U first. Delta U is Q plus W. Go write a statement about Q, go write a statement about W, gonna make a conclusion about delta U. Something like that lah. Okay, what do I know about all these three first? Number one, it's evaporating. So there is a state change. Correct? Evaporate ma? Liquid to gas. If there is a state change, the potential energy will increase because the bonds are stretched. Particles are further apart. In chemistry or basic science, you would have memorized the explanation as to why heating and melting happen at a constant temperature. This is, boiling and melting happens at a constant temperature. This is because the heat is used to break or to loosen the bond. The so-called break the bond basically means increase the potential energy. So the energy that heat has given to you is used to increase potential energy and not kinetic energy. So if EP increase, but EK constant-ish, but very hard to say is evaporation. So now let's not comment about the temperature. I don't know. Actually, never mind. The one thing too much. EP increase, delta U increase. Or U increase. So delta U is positive. If it's evaporating, surely there is some heat absorbed or thermal energy. Mark scheme tend to use thermal energy. Thermal energy absorbed from surrounding. Positive Q. W leh? Wow, this one work done by the gas evaporate ma as it expands against the atmosphere. Negative W, expand against the atmosphere. So right now, I need to be able to justify why delta U is positive. I cannot justify using potential energy because this potential energy is not first law. Because it's not first law, I mention it also won't get marked lah. I won't be penalized as long as my scientific facts are correct, but I also won't be awarded credit. Which also means if I want to explain from the perspective of internal energy, what I will need to argue is that, so based on the fact that this one must be positive, that means positive Q must be greater than negative W. So I will say that the work done by the gas is less than the heat, thermal energy absorbed from surrounding. So internal energy increases. I'm kind of like going through an alternate route to argue my point by sticking to the first law of thermodynamics. But if during the exam you have extra lines, I will also say during state change, the potential energy between the water molecules increases. I mean the kind of state change lah. So if you're using solid to liquid, to gas in this direction, the potential energy increases. This is the alternative part. If potential energy increases, internal energy is equal to KE plus PE. PE increase, internal energy increase. So if you write things that are not related to the first law, there will be no credit one. The thermal energy absorbed equal to the latent heat of vaporization. This one, yes, but writing it doesn't give you any marks for this question. This Q is equal to ml. But, wait. But this is for boiling only. This is not boiling, it's evaporation. So don't use. Because you can only use latent heat. Latent means no change, right? Only if the state change is at constant temperature. So no, this internal energy is not equal to ml. Next one. Can I put work done by gas to overcome surface pressure? What is surface pressure? If it's a chemistry term, I would suggest that you don't. So for physics, we always think from the perspective of the atmosphere. The gas will expand and push against the atmosphere. If it's the surface pressure due to the hydrogen bonds, just think about how your physics teacher will never use those words to explain this. So don't. Push against the atmosphere. External pressure also can. Surface pressure is not a known term for us, unless we remember our chemistry, which is always a hit or miss thing, so don't. Okay, last call. Any other follow-up things you want to clarify tonight, based on what we've discussed so far? So my only advice for you, since we've been together for a better part of almost 4 months, 4-ish months, is that you do what you can. So you ought to have like an idea about, okay, this is the scope of paper 4. It consists of this many chapters. Here are the chapters that I'm more confident about. You can put one side, put in your back pocket. Okay. Here are some chapters that I'm getting better at. So maybe you can spend this weekend to go through some questions. And here are the chapters that I struggle with. So work on the middle, the one that you are getting better at. Okay. The struggle ones, if really too difficult, it's okay to let it go. Okay. Generally speaking, if you get around 70 out of 100, it's a pretty good score. Okay. But that being said, the only way to get good is just to do more questions or increase your experience point and give yourself enough breaks in between trying. My comment for paper 4 is still the same for paper 5. But paper 5 is a skill-based paper. So you can watch the recording about my comments about how to build the skills and practice. Paper 5 is a practice paper. I think I've also shown you this before, in case I haven't. Here's where it is. If you kick the Cal resource folder, there's a paper file. Okay. You can download this one. You just save your own copy now. Okay. You click like that and then you want to download. Okay. So when you download it already, what you will see is something like this. Okay. So I have already rank sort all the question until winter 23. Okay. And let's say you want to study, the way I'll do it is every day I study a few experiments. Let's say I want to study the AC experiment. How would the AC experiment look like? Do I even know how to draw a circuit? Okay, now I press AC. And then after that, I filter column E. All the experiment with AC will come out. We'll go study lah. So choose one or two variables to study. There's one way to go about it. You could also actually this one is the same. I'll check later. You could also look at instrument. For example, you go like, I wonder how an experiment about Hall probe can look like, and do I even know how to write a Hall probe experiment? Same thing, lor. You filter for one. Here are some experiments. Here are the years. Go study. That's all. Remember the format, follow the format, know how to measure stuff, know how to draw them together in a diagram. It's good enough for question 1. Question 2, know how to find uncertainties in many, many situations and handle the linearization of graph. That's all for paper 5. Go practice. It's a practice paper. So download your own one. You can filter yourself if you want to. There are some questions here, but I will not really be looking at this now. At this point, I will just look at past years and pick and choose some to do. Okay? In other words, there is no shortcut lah, sorry. Or at least if there is, I don't. Besides just working a bit smarter. Okay, I will see you when I do. And if I don't, all the best for you in your future. It'll be okay. Okay, whatever happens, you have done what you can. And the world is a big, big place with many, many different kind of opportunities. And we never know where certain places will lead us, even into places that we can't imagine. So all the best lah. Be nice to yourself. Any questions, you can send them to me in chat. I will try to answer them before your paper. But please rotate your question lah. Rotate. You don't rotate. I look at my phone. I'm like, I don't know how to see. Rotate your question. Okay. All right. Good night now. Bye-bye. All the best. Take care. And thanks for joining class. I hope your future will be as bright as you are. Bye.
Bye-bye.
Bye-bye. Thank you.
Thank you.
See you.